Okay, so this example is one of the examples I used in the research project, the online tasks that you guys completed. And it was about introducing how to use this tool, using the context of the six-sided dice that potentially might be a bit dodgy, a bit shonky, that was bought from Tillers store. So the idea is on the left-hand side you have the real situation, which involves a description about the situation and then deciding what the variable is. And in this case here, it's the number that lands face up on the dice. In an earlier version of the simulation tool that I developed last year, one of the teachers who was trying it out for me wanted the variable description to be compulsory so that students couldn't progress further with using the tool unless they defined the name of the variable. So you'll find that if you try to generate any data or go any further, a pop-up will say, you need to include the description of the variable before you go further. The reason why I've used dice, even though dice is kind of like such a common thing that we use in teaching probability, is that although I'm going to demonstrate using the software straight away, you could of course use dice as a hands-on simulation first to investigate the same situation, and then use the software as a way of mimicking what you're doing with the hands-on simulation. Anyway, so the idea is that someone has rolled this dice 20 times, and they have observed that on 9 of those 20 times, the dice has come up as a 6. So what we want to do is put this data into the tool. So if it's just individual values like that, we can enter them in as individual values separated by commas. I'm doing this slowly just so that you can see. 2, 6, 5. I hope that's all the values. We'll see in a moment. And then what happens on this tool actually is that as soon as you put the data in and kind of, get out of there, you'll see that a dot plot will be produced of that data, and you can see there's 20 values there, so I had to mark that up. Okay, so I've specifically used quite a small sample for this example, because we want students to see or expect quite a large amount of variation when in the shape of the distribution, or in this case here, the proportions or the counts that go with each of the outcomes that we'd expect on a fair die, that there'd be a lot of variation from sample to sample. We'll come back to the bottom screen in a moment. Okay, so this idea was we want to set up a model on the right-hand side for the situation. In this case here, it's more like a kind of we're setting up sort of like a null, I suppose, what's how assumed. So let's assume that it's a fair die, and if it was a fair die, then we're looking at a uniform discrete variable with values that go from 1 to 6. And what I've done here in this panel here is what you want to do is generate the same number of values from this distribution as what was observed in the sample distribution. In this case here it's 20. So if we run 20 values, there might be a slight adjustment in terms of the size of the dots. I've set it up so that whatever's on the right-hand side panel is on the left-hand side panel in terms of the size of the dots. And that's so that we preserve that proportionality comparison between the two panels, the real data and the simulated data, because you'll notice I'm not using an axis scale or anything like that at all. Okay, so what we can see here is this is a simulated set of 20 values from a uniform discrete distribution, and it doesn't look that similar to that. What we want to do is build up an idea of what the shape of the data distribution could look like from this model for this amount of data. So actually, if I just press the start animation just to show you this feature, what this is going to do is repeat the simulation until you tell it to stop. So it's going to just keep generating sets of 20 values from this uniform discrete model. And again, this is to show students just the kind of variation that we could expect from sample to sample in terms of what outcomes we get. So we don't always get one of every possible outcome, and the varying heights, which is the observed proportions of each of these outcomes. So the thing about tracking shape is that it's hard maybe for students to remember some of the stuff, even though we're showing them repeated simulations. So I'm just going to pause this for a second. So what I've got down here is these features below here where you can capture stuff. So I'm going to focus, oopsie daisy, I'm going to focus on checking the overfitted shape, and I've called it the overfitted shape in this last version of the tool, because basically I'm just going to go from the top of every single dot and make a line graph basically from those values. So if I pop that on and then start the animation, what you'll see now is that every time that a new simulation generates a set of data, we'll leave behind the overfitted shape. It's got a slight transparency to the lines that you can see where things build up, and particularly what you would expect to see in this case here, because it's only 20 values, is that it's kind of all over the place. So what we need to do though is help students decide what to do in this situation. If we just left it at, well, it's only 20 values, you know, you can't say anything because the sample size is too small, well, that's only kind of part of the story. In this case here, I've let it run for a little while. What I can do is I can transfer over this build-up of the shape. So first of all, it's really thick because there is a lot of uncertainty involved because the sample is so small. If I transfer that over, what I can see is that, and in these cases here, in the simulations that I've run, I didn't, in this case, ever get this many values, 9 values, coming up as a 6. Now, of course, we know as teachers that, you know, over here, there's 2 to get pretty high, and actually that's kind of equivalent because really, we're really testing whether any one of those values could be as high as that. Yeah. But anyway, I don't want to get too technical about it because that's not the point of this tool. We're not doing officially or formally doing a goodness of fit test, and what we really want to build up with students is this idea that, okay, yep, I can take into account the amount of data when I'm looking at something like the shape or the underlying distribution when considering possible models. And in this case here, it's not looking like, even if we look at how much the values could jump around from sample to sample, it's not looking like a uniform or a fair dice is matching up with the situation or the data that we observed from the situation. Again, if we contrast that example with one where there's quite a bit more data, so if I pull up the London bombing example that was used in the online tasks or the research project, and this one's a kind of a classic example. You can find tons of other resources online that kind of go through the same scenario. So this is the idea around whether the bombs that were being dropped, whether they're being targeted at particular places in London, or was it sort of somewhat random where they ended up. And so that's why you've got the number of bomb hits per half kilometre square area. And again, this is the raw data. And you can see in this case here, I have entered it all individually. That was before I changed one of the features that allowed you to enter in the data as frequency data. But anyway, okay, so what happens with my tool is basically you can't ever have the dots size so much that they go off the screen, so it gets to a certain point where they get pretty small. You can't really see them anymore, but that's just how it is at the moment. I haven't pulled a way around that just yet. Okay, so this is the data here, and in this case you've got 586 values, and the question would be, well, you know, could a Poisson model be a good model? But really what we're asking is could this data have been generated from a Poisson distribution model, or sorry, does it look similar to data generated from a Poisson distribution model, in which case we might consider that the bombs were being dropped in a somewhat random manner. Okay, so what we can do this time is use one of these other features down here, which is we can look at what the mean is by clicking on that. And some of this rounding stuff is a little bit weird. Some weird stuff happening in JavaScript, which is the code, the program language I'm using to do this stuff around working with numbers. But anyway, I'll try to fix it. Anyway, so it's around about 0.92. So what we could do is set up a Poisson model using that estimate there for our lambda value. And again, what we can do is generate the same number of simulated data values as what we observed. And what you see in this case is the same thing. You don't really get to see the dots again. And all really is looking pretty similar in terms of the shape. Not identical, but maybe similar enough. But again, we want the students to kind of see how much the shape of this distribution could vary from sample to sample, and you see there is still some jumping around there, and again if we track it, what we see pretty quickly this time is that we're not getting so much of a mess. Our grey area, the overfitted shape, is not as, the band that's being formed by tracking it is not as wide. Which is again showing us that these proportions that we're going to observe aren't going to vary by as much as when we looked at that dice example. And again, this is all informal, so you could get the kids to count how many times it's a run through if you wanted to, or not. Sometimes I've left it on by mistake and come back and it's it's done probably thousands, but anyway, I'm going to stop it there. And again, what I'm going to do here is say, well, look, this is the kind of, if this was my model, this is what I could expect to see in terms of the shape when I'm generating, or when I'm looking at 586 values. If I transfer that over, I can see that it's looking like it's pretty good. It's a pretty good fit. And so I might say, well, it looks plausible that a Poisson model would work. Now the thing is, this is just me being a little bit more specific, is that I've used 0.92 here, but actually, if I was to use 0.91 and generate it based on 0.91, I'm actually going to get a similar, oh, I left that on, I'm going to get a similar kind of story really in terms of building up the track shape over here, and it's going to look like it's pretty close over here. And the reason for that is because, of course, we've built our model here on a sample mean. We've used the mean of this observed data here, and of course, as we know from all the work we've done on inferential reasoning and those pathways, is that, of course, if we were asking students to estimate the underlying population mean based on that sample mean, they would be thinking of the cognitive interval. And so, you know, there are some ideas there that would be linking between those stands. We don't need to make a big deal about it, but it is just something that would be quite nice to show students that actually, here, look at this one, I've used a slightly different mean, but again, if I was to track the similar data based on that model and then transfer it over, it's looking like it's pretty good as well. I guess just one thing to watch out for in terms of this modelling process is that in this case here, I've set up a model, I've generated data from it, and it does look like it kind of fits the situation. That doesn't prove that this is the model, it doesn't prove that this is how the data is being generated. It just shows that a model like this could generate similar data to what we've observed. Okay, obviously the people flying the planes weren't, it wasn't a Poisson distribution that was telling them how to drop their bombs where they wanted to. And that sounds silly, me saying that now, but we do need to be careful that we don't kind of build these ideas that the data itself does actually come from a particular distribution. It's a model for what we're seeing. I'm going to show you one more example before this video becomes ridiculously long. Under here I've put in some other data sets. So for example, I've put in here some of the data that was used in the last 3 years of exams. This one here, if you go back to that question, you need to go back to the question to read the full story. This was about this high performance player, I think it was a squash player, and how long their matches were in minutes, and whether the normal distribution is good. Well, now, you'll notice when you look at the question that the data is presented in a histogram, and so you just get the class intervals and the, well, actually you don't get any information. Oh no, so you get the class intervals and you get the proportions that were observed for each of those bins in the histogram. And my tool's set up to work with individual values, not grouped values. So in the notes I've sent you, you'll see there's instructions for how to enter in grouped data. Basically, you put in the limits of each interval and you put in the frequency, and what my tool will do is generate, using a uniform continuous distribution, that many values between those limits. It's not perfect, but it's a way to get a dot plot of the situation. Okay, so this is what I've got here, is a sort of representation of that data. And what you notice at the bottom, and I rounded it to the nearest 5 because That was